What if everything we think we know about space, about our place in the universe, about what's possible, is just the beginning? Right now, scattered across the globe and beyond it, scientists and engineers are working on missions so ambitious, so daring, they could rewrite the future of humanity itself. Picture this: robots tunneling through the icy crust of distant moons in search of alien life, spacecraft harnessing the power of the sun to sail beyond our solar system, and plans so bold they might one day turn Mars into a second home for us all. This isn't science fiction. These are real projects, real blueprints, real countdowns already in motion. And today, we're diving into 30 of the missions that could change everything. Think about how far we've come in just a handful of decades. We've landed on the moon, sent probes to the edge of our solar system, and glimpsed the birth of galaxies billions of light years away. But what's coming next? What's being dreamed up in labs and whispered about in mission control rooms? The answer is unfolding right now in ways that will make our current era look like a prologue. Some of these missions aim to crack the mysteries of dark matter or hunt for signs of life on Europa's hidden oceans. Others are laying the groundwork for cities in space or preparing to send humans farther than we've ever gone before. Each one is a piece of a puzzle that, when solved, could redefine not just science, but what it means to be human. This is more than just a list of rockets and launch dates. This is about the tipping points, the moments when a single mission could flip our understanding of the cosmos on its head. Maybe it'll be the discovery of a microbe on Enceladus, or the first successful test of a warp drive, or even the day we hear back from an AI probe sent to another star. Whatever it is, the ripple effects will touch every one of us, so buckle up, because over the next 30 missions, we're going to explore the edge of what's possible and maybe, just maybe, catch a glimpse of the future we're all hurtling toward. Mission 1 brings us back to the moon, but not the way we remember it. NASA's Artemis program isn't just a redo of Apollo. It's the first step toward turning humanity into a multi-planet species. By 2025, astronauts will touch down near the lunar South Pole, a region packed with shadowed craters hiding water ice, a resource that could fuel rockets, quench thirst, and even breathe life into future colonies. But Artemis isn't just about footprints this time. Orbiting above will be the Lunar Gateway, a cutting-edge space station serving as a pit stop for crews traveling between Earth and the Moon. Think of it as a cosmic gas station where missions can refuel, swap gear, or even assemble spacecraft bound for deeper space. And here's where it gets really ambitious. Those first lunar habitats won't be temporary tents. Engineers are designing structures that could last decades, shielding astronauts from brutal radiation and temperatures that swing from scorching to bone-chilling in hours. Some prototypes use 3D printers to turn moon dust into walls, while others inflate like high-tech balloons. It's all a dress rehearsal for Mars. Every solar panel deployed, every water extractor tested, is a lesson in how to survive on a world where help is millions of miles away. Right now, teams are rehearsing in deserts and underwater labs, simulating lunar conditions as new spacesuits sleeker, more flexible than the bulky Apollo gear, get put through their paces. And the landers, they're engineering marvels, with SpaceX's Starship and Blue Origin's Blue Moon competing to ferry crews to the surface. This isn't just about planting flags anymore. It's about laying foundations, because when those habitats go up and the gateway starts humming, the moon stops being a destination and becomes a springboard to the stars. While the moon serves as our stepping stone, Mission 2 takes us millions of miles farther, to the rust-colored deserts of Mars. Right now, NASA's Perseverance rover is scouring Jezero Crater, a dried-up lakebed, drilling into rocks that may hold the secrets of ancient life. But here's the catch: those precious samples are stuck there, trapped in titanium tubes scattered across the Martian surface. That's where the most complex interplanetary relay race in history comes in: the Mars Sample Return Mission, a staggering collaboration between NASA and the European Space Agency. The plan reads like a sci-fi heist. First, a tiny helicopter, similar to Ingenuity but beefed up, will scout the best paths for the sample fetch rover, a nimble robot designed to race across Mars, scooping up Perseverance's tubes like a cosmic treasure hunter. Once collected, they'll be loaded into a basketball-sized container aboard a rocket no bigger than a lawn chair. Yes, a rocket launching from Mars. This pint-sized powerhouse will blast the samples into orbit, where a waiting spacecraft will snag them mid-flight and hurtle them back to Earth. If it works, it'll mark the first time we've ever brought pieces of another world home in pristine condition. But why go through all this trouble? Because locked inside those samples could be biosignatures, chemical whispers of life that vanished billions of years ago. Earth's geology constantly recycles itself, erasing its earliest history. Mars, though, froze in time. Its rocks might preserve evidence of microbial organisms that thrived when water still flowed there. And unlike rover labs, which are limited to a few instruments, labs on Earth can bombard these samples with every tool imaginable, from atom-smashing particle accelerators to DNA sequencers sensitive enough to spot a single strange molecule. The stakes couldn't be higher. A single grain of sand might rewrite biology textbooks, proving we're not alone in the universe, but the mission's complexity is mind-bending. Each step, the rover's precision driving, the rocket's flawless launch from another planet, the orbital handoff, has to go perfectly. One glitch and decades of work could vanish into the Martian dust. Yet if it succeeds, those tiny tubes won't just hold dirt. They'll hold answers to questions we've asked since we first looked up at the red dot in the sky and wondered, was there ever life out there? Now imagine a telescope so powerful it can peer back in time, catching the faint glow of galaxies born just a few 100 million years after the Big Bang. That's the James Webb Space Telescope, a golden-eyed marvel orbiting 1 million miles from Earth, where the cold void of space helps it detect whispers of heat from the distant cosmos. Unlike Hubble, which sees mostly visible light, Webb specializes in infrared, letting it cut through cosmic dust like night vision goggles piercing fog. And what it's found already is rewriting the playbook of astronomy. Take exoplanets, for instance. Before Webb, studying their atmospheres was like trying to identify a candle's color from across a football field. Now, Webb can dissect the light filtering through alien skies with precision, sniffing out molecules like methane, carbon dioxide, and, in the case of the Haitian world, K218b, even hints of dimethyl sulfide. On Earth, that's a gas only produced by life, mostly plankton. Could it be a biosignature? Too soon to say, but Webb's data has scientists buzzing. Then there's WASP-96b, a scorching gas giant where the telescope spotted clouds made of sand, yes, literal sand, floating in a sky hotter than lava. But Webb's reach stretches far beyond exoplanets. It spotted galaxies so old and massive they shouldn't exist under current theories, cosmic toddlers that grew up too fast. One, named Glass Z13, formed when the universe was just 300 million years old, a toddler in cosmic terms, yet it's already sprawling with stars. How? Nobody knows yet. Every new image is a puzzle piece, and some don't fit the picture we thought we had. Then there's the drama closer to home. Webb's snapshots of Jupiter reveal auroras dancing at the poles, while its study of Uranus shows the icy giant's faint rings in shocking detail. Even dying stars get a close-up. The Southern Ring Nebula, a kaleidoscope of gas ejected by a fading sun, looks like a glitter bomb frozen mid-explosion. What makes Webb so revolutionary isn't just its tech, though its 18 hexagonal mirrors, each plated in gold thinner than a human hair, are feats of engineering. It's the questions it forces us to ask. Are we alone? How did the first stars ignite? And what else is out there, lurking in the infrared shadows, waiting to be seen? Every answer Webb delivers seems to sprout 3 new mysteries, and that's the point. Because in the end, the universe isn't just stranger than we imagine, it's stranger than we can imagine. And for the first time, we've got a front row seat. Beneath Europa's cracked, frozen shell lies one of the most tantalizing mysteries in our solar system, a vast, swirling ocean with twice the water of all Earth's seas combined. NASA Europa Clipper, set to launch as soon as 2024, isn't just another spacecraft. It's a detective armed with tools designed to sniff out the secrets of this alien sea. Imagine flying a probe over Antarctica, but instead of ice below you, there's a dark, saltwater abyss stretching hundreds of miles deep and possibly teeming with life. That's the gamble scientists are taking. The Clipper won't land. Instead, it'll perform a delicate dance around Jupiter, swinging past Europa 45 times to map its surface in unprecedented detail. Its ice-penetrating radar, REASON, can peer through up to 18 miles of ice, hunting for liquid pockets or plumes erupting into space. Think of it like ultrasound for a moon, every scan revealing fractures, brine channels, or even the thickness of the ice shelf separating the ocean from the vacuum above. And then there's the surface dust analyzer, ready to catch particles ejected from those plumes. If organic molecules building blocks of life are hitching a ride on those geysers, this instrument will flag them. But why Europa? Because it ticks every box for habitability. Liquid water, chemistry from tidal heating, and energy sources from hydrothermal vents that might mimic Earth's deep-sea oases. Some models suggest its ocean floor could be dotted with vent-spewing minerals, a buffet for microbes. And those infamous plumes, they're Europa's way of serving samples on a silver platter. In 2013, Hubble spotted what looked like water vapor bursting from the South Pole. If Clipper confirms these eruptions, future missions might fly through them, tasting the ocean without drilling through miles of ice. The stakes astronomical. Finding even simple organisms here would prove life isn't a fluke of Earth, it's a cosmic inevitability. But Europa is no gentle target. Jupiter's radiation belts bombard the Moon with lethal particles, forcing Clipper to duck and weave between orbits. Every pass is a race against time, its instruments shielded by a vault of titanium just to survive. Yet if it succeeds, Europa's secrets could redefine where we look for life, not just in our solar system, but around distant stars with similar icy worlds. Suddenly, alien might not mean little green men. It could mean something stranger, older, and waiting in the dark beneath the ice. Mission 5 takes us to a world where rivers carve valleys not in rock, but in ice, where the sky rains methane and the ground is littered with organic dunes as tall as skyscrapers. This is Titan, Saturn's largest moon, and NASA's Dragonfly mission is about to turn science fiction into reality. Forget rovers plodding across dusty plains. Dragonfly is a nuclear-powered rotorcraft drone designed to fly across Titan's thick atmosphere, hopping from one site to another like a robotic explorer on wings. Titan is Earth's twisted mirror. It has weather, shorelines, even seasons, but swap water for liquid methane and sand for hydrocarbon grains. Dragonfly's job: to hunt for the chemistry that might have sparked life on Earth billions of years ago. Its landing zone, the Shangri-La Dune Fields, a sprawling wasteland of organic particles that rain from the sky mixed with icy bedrock. Here, the drone will use its 8 rotors, each nearly 3 feet long, to lift off in Titan's low gravity, soaring miles at a time to sample sites where sunlight and cosmic rays have baked these organics into complex molecules. But the real magic happens in Dragonfly's belly. Its mass spectrometer, nicknamed Artemis, will vaporize samples and sift through the fumes, hunting for amino acids or other building blocks of life. Then there's the gamma-ray spectrometer, which can peer beneath the surface to spot reservoirs of liquid methane or ammonia hiding just inches underground. And because Titan's atmosphere is 4 times denser than Earth's, flying here is oddly energy efficient, like swimming through syrup. A single charge from its plutonium battery could keep Dragonfly aloft for hours, covering more ground in a day than a rover might in months. Why Titan? Because it's a frozen time capsule of probiotic chemistry, a lab where nature has been running experiments for eons. The methane lakes, they're not just fuel for hypothetical life. They're solvents stirring and mixing molecules in ways water might have done on early Earth. The dunes, they're archives, layers of organic gunk that could hold clues to how complex chemistry emerges from simple ingredients. And Dragonfly's flights aren't just about distance, they're about time. By visiting sites of different ages, it can piece together how these reactions evolve over centuries. The challenges are surreal. At -290 degrees Fahrenheit, Titan's cold is brutal enough to freeze rubber solid. Yet Dragonfly's cameras will snap panoramas under an orange haze, while microphones capture the sound of wind whistling through icy canyons. Every hop is a gamble, with terrain maps pieced together from decade-old Cassini data. But if it works, Dragonfly could uncover something revolutionary, proof that the steps toward life aren't unique to Earth, that in the methane slush of a distant moon, the universe might be quietly repeating its greatest trick. Venus has long been the solar system's cautionary tale, a planet once thought to be Earth's twin, now a hellscape of crushing pressure and acid clouds. But two daring missions, Veritas and DaVinci Plus, are about to crack open its secrets. One will scan the surface like never before, the other will plunge straight into the storm, and together they might finally answer a haunting question: did Venus almost become us? Veritas is a masterclass in planetary detective work. Orbiting high above those toxic clouds, it'll wield radar so precise it could spot a parking lot on Earth from space. But here's the twist: Venus's surface is constantly reshaped by volcanic eruptions and tectonic forces. Some scientists suspect it might even have plate tectonics, just slower and weirder than Earth's. Veritas will hunt for the scars. Lava flows younger than a few thousand years, fault lines where the crust grinds, or even hotspots hinting at active magma chambers. Imagine mapping a puzzle where every piece is on fire and you start to grasp the challenge. Then there's DaVinci Plus, the daredevil of the pair. While Veritas observes from a safe distance, DaVinci probe will dive headfirst into Venus's atmosphere like a robotic skydiver, tasting the air as it falls. For 60 terrifying minutes, it'll battle winds that scream at hurricane speeds, measuring how much water vapor, noble gases, and sulfur compounds are swirling in those yellow clouds. And right before it's crushed by pressure 90 times Earth's, its hardened camera might snap the first clear photos of Venus's mysterious tesserae, a jumbled highlands that could be continents from a lost ocean. Why the two-pronged attack? Because Venus's past is a cosmic cold case. Billions of years ago, it might have had oceans, temperate skies, even a magnetic field. Then something triggered a runaway greenhouse effect, boiling its seas and turning the air into sulfuric acid. Veritas could spot the smoking gun volcanoes that belched enough CO2 to tip the balance, or evidence of a catastrophic resurfacing event. Meanwhile, DaVinci chemical fingerprints might reveal how much water Venus truly lost, and whether its atmosphere once rippled with storms like Earth's. The implications are staggering. If Venus was habitable, and if we pinpoint why it wasn't, we'd have a blueprint for what can go wrong on an Earth-like world. That knowledge could be the difference between thriving on Mars and watching it become another Venus. These missions aren't just about the past, they're about every future we're trying to build. Deep in the asteroid belt between Mars and Jupiter, a world unlike any other spins silently in the dark, an object so strange it might be the shattered heart of a failed planet. This is Psyche, a 200-mile-wide hunk of metal that could hold the keys to understanding how rocky worlds like Earth are born. A mission to this metallic anomaly isn't just another spaceflight. It's a journey into the solar system's violent past, where collisions and chaos shape the planets we know today. Most asteroids are rubble piles or icy leftovers, but Psyche gleams differently. Radar scans suggest it's packed with iron, nickel, and possibly gold enough to make every person on Earth a billionaire if mind not that we could haul it back. The wildest theory, Psyche might be the naked core of a protoplanet, stripped of its rocky shell by ancient cosmic crashes. Imagine cracking open Earth and finding its molten heart frozen in space. That's the level of discovery we're talking about. The Psyche spacecraft, launching in 2023, will spend 2 years orbiting this metallic relic, armed with tools to solve the mystery. Its magnetometer will hunt for traces of a fossilized magnetic field, a smoking gun that this was once a dynamo churning in a young planet's core. The gamma-ray spectrometer will map the asteroid's composition down to individual elements, revealing whether it's truly solid metal or riddled with unexpected voids. Even Psyche's gravity field will tell a story. Slight tugs on the spacecraft could betray underground caverns or dense pockets of precious metals. But why does a hunk of space metal matter? Because we've never touched a planetary core. Earth lies thousands of miles beneath our feet, crushed under impossible pressure. Psyche offers a shortcut, a chance to study core chemistry up close. If it's truly a fossil core, its structure could reveal how planets like ours differentiate, with heavy metals sinking to the middle while lighter rocks form the crust. Alternatively, Psyche might be something weirder, the remnant of a metallic volcano that erupted in the early solar system, or a rare survivor from a class of objects that mostly vanished. Every pixel of data from Psyche's cameras will rewrite textbooks. Its surface could be studded with metal spikes from eons of impacts or flow patterns etched by long-cooled rivers of liquid iron. Some models even suggest metallic lava might once have oozed across its landscape under a sky of molten metal vapor, and if Psyche still crackles with remnants of magnetism. That would hint at a once active core frozen in time like a stopped clock. This mission isn't just about the past. Understanding how metals behave in space could revolutionize asteroid mining. Future prospectors might target Psyche like bodies for resources. More profoundly, it forces us to rethink how planets assemble. Maybe collisions aren't just destructive, maybe they're creative acts, forging new worlds from the shrapnel of old ones. By the time Psyche's engines fire for their final approach, we won't just be exploring an asteroid. We'll be reading the autobiography of the solar system, written in atoms of iron and whispers of lost magnetism. Floating between the Moon and Earth, a futuristic outpost is taking shape, one that could change how we explore deep space forever. The Lunar Gateway isn't just another space station. It's a cosmic pit stop, a jumping-off point for missions to Mars and beyond. Unlike the International Space Station, which orbits just 250 miles up, Gateway will loop around the Moon in a halo orbit, a delicate dance between Earth's and the Moon's gravity. This position makes it the perfect staging ground. Need to prep a lander for the lunar surface? Gateway's your workshop, assembling a ship for the 8-month trek to Mars. Its docking ports will buzz with activity. At its core, Gateway is a modular masterpiece. First up, the Power and Propulsion Element, or PPE, a solar electric powerhouse with thrusters 10 times more efficient than traditional rockets. Unlike the ISS, which relies on frequent resupply missions, PPE's ion engines use xenon gas and sunlight to nudge Gateway into position, conserving precious fuel. Then there's Halo, the habitation and logistics outpost, a compact living quarters where crews will test tech for surviving far from Earth. Picture a high-tech camper van, packed with life support systems that recycle air and water with near-perfect efficiency. Early astronauts might only stay weeks, but every hour logged here is a rehearsal for Mars, where resupply isn't an option. But Gateway's real genius lies in its flexibility. Future modules will include a European-built refueling depot and a Canadian robotic arm for assembling deep spacecraft. Scientists are even planning a biology lab to study how radiation and low gravity affect human cells, critical data for shielding Mars-bound crews. And here's the kicker: Gateway isn't just a NASA project. The European Space Agency, Japan, and Canada are all contributing hardware, making this the first true international hub beyond Earth's orbit. The station's location unlocks another advantage. From its unique vantage point, Gateway can host telescopes shielded from Earth's radio noise, peering into the cosmic dark with unprecedented clarity. Astronauts might remotely operate rovers on the Moon's far side, exploring regions we've only seen from orbit, and for Mars missions, Gateway becomes a proving ground. Want to test a new spacesuit's durability? Try it on a spacewalk here, where radiation levels mimic the journey to the red planet. Need to practice docking a lander. The Moon's gravity well is a safer training ground than Earth's. Yet Gateway's ultimate legacy might be psychological. For the first time, humanity will have a permanent foothold in deep space, a place where the Earth is just a blue dot in the window. Every crew that cycles through will push the limits of endurance, teamwork, and tech, paving the way for those who will go farther. It's not just a station. It's a statement. We're not stopping at the Moon. We're using it as a springboard to the stars. Imagine a rocket so powerful it could lift a fully loaded space station in a single launch, and then land itself back on Earth to fly again. That's SpaceX's Starship, not just a spacecraft but a revolution in how we reach space. Towering nearly 400 feet tall, with engines capable of hurling 150 tons into orbit, Starship is designed to be fully reusable, turning aerospace economics on its head. While traditional rockets are demolished after one use, like throwing away a jumbo jet after a single flight, Starship's stainless steel hull and methane-fueled Raptor engines are built to be refueled and relaunched within hours. The goal: slashing the cost of reaching orbit from thousands of dollars per pound to mere hundreds. But Starship's real magic lies in its versatility. Need to deploy a fleet of Starlink satellites in one go? Starship's cavernous payload bay can swallow entire constellations. Dream of lunar bases? NASA already contracted it as the human landing system for Artemis, ferrying astronauts from lunar orbit to the Moon's surface and back. And Mars? Elon Musk's vision hinges on Starship's ability to carry 100 settlers at a time, with onboard refineries turning Martian CO2 and ice into return trip fuel. The audacity of the plan is matched only by its engineering. Watching Starship prototypes test fly is equal parts awe and chaos. Early flights ended in fireballs, some by design, as SpaceX embraces a fail fast, learn faster approach. The infamous SN-15 prototype soared 8 miles high before flipping belly down and sticking its landing, proving the spacecraft's belly flop maneuver could work. Later tests pushed boundaries further, with orbital attempts showcasing the Super Heavy booster's 33 Raptor engines roaring in unison, generating thrust twice that of the Saturn V. Every explosion teaches engineers something new. Every successful hop inches humanity closer to interplanetary travel. Critical to Starship's long-haul ambitions is orbital refueling, a feat never attempted at this scale. The plan reads like a cosmic ballet. One Starship docks with another in orbit, transferring cryogenic methane and oxygen to top up tanks before venturing deeper into space. Without this, Mars missions would require impractical amounts of fuel at launch. SpaceX envisions tanker Starships making multiple trips to fill a waiting Mars-bound vessel, creating a chain of celestial gas stations. The implications are staggering. If Starship delivers on its promises, a single launch could cost less than $10 million, cheaper than some Hollywood films. Suddenly, mega-constellations, space hotels, and even asteroid mining become financially feasible. Critics argue the timeline is optimistic, pointing to regulatory hurdles and unproven tech. But SpaceX's track record speaks for itself. Falcon 9's reusability was once dismissed as fantasy, yet its boosters now land with the routine precision of commercial airliners. Starship isn't just a rocket. It's a bet on a future where space isn't the exclusive domain of governments but a frontier open to anyone. Every stainless steel ring welded in Boca Chica, every Raptor engine tested in Texas, is a step toward a solar system where humanity isn't confined to Earth. The question isn't whether Starship will change space travel, it's how soon and how profoundly. While SpaceX's Starship grabs headlines with its Martian ambitions, Blue Origin has its sights set firmly on the Moon, not just to visit but to stay. The Blue Moon lunar lander isn't just another spacecraft. It's the cornerstone of Jeff Bezos's vision for a future where millions live and work in space. At first glance, it seems like a direct competitor to SpaceX's Starship lunar variant, but dig deeper and you'll find a radically different philosophy at play. Blue Moon is lean, precise, and laser-focused on one goal: becoming the UPS truck of the Moon, delivering cargo, habitats, and eventually cruise with clockwork reliability. The lander's secret weapon, its B7 engines, which burn liquid hydrogen and oxygen fuel so cold it's just degrees above absolute zero. Cryogenic tech like this is notoriously finicky. Hydrogen atoms are so small they can leak through solid metal, but the payoff is immense. Hydrogen packs more punch per pound than any other rocket fuel, and when it burns with oxygen, the only byproduct is water vapor. That makes the B7 not just powerful, but clean, a critical factor for sustainable lunar operations. Blue Origin has already put these engines through hundreds of test firings, including a record-setting 125-second burn that proved they could handle the Moon's harsh thermal swings. But Blue Moon isn't going solo. NASA tapped it as the second human landing system for Artemis alongside SpaceX's Starship. Here's where the contrast sharpens. While Starship is a massive, all-in-one vehicle designed for Mars-scale missions, Blue Moon is modular. The base version is an uncrewed cargo hauler capable of delivering up to 3 metric tons to the lunar surface. Need more? Dock additional descent stages in orbit, scaling up to a crewed version that can carry 4 astronauts. This Lego brick approach lets NASA mix and match, using Blue Moon for targeted science missions while reserving Starship for heavyweight lunar base construction. Partnerships are key to Blue Origin's strategy. The company has teamed up with Lockheed Martin, Draper, and Boeing to refine Blue Moon's navigation systems, leveraging decades of aerospace expertise. Lockheed's contribution, a single-pin docking system that lets landers connect autonomously, even in the Moon's low gravity. Draper is adapting Apollo-era guidance tech for precision landings within meters of target sites, crucial for avoiding treacherous craters near the lunar poles. And Boeing's CST-100 Starliner capsule could eventually ferry crews from lunar orbit to the surface, creating an end-to-end transportation network. The lander's design reflects hard lessons from history. Its oval-shaped cargo deck, suspended above the engine cluster, avoids the dust cannon effect that plagued Apollo landings, where rocket exhaust kicked up debris at dangerous speeds. Instead, Blue Moon's engines are recessed, with exhaust vents angled outward to minimize surface disruption. That's vital for preserving delicate lunar ice deposits, which future colonists will rely on for water and oxygen. Even the landing legs borrow from nature, with shock-absorbing honeycomb structures inspired by beetle wings. What truly sets Blue Moon apart, though, is its long-game mindset. While Starship aims to make humanity multiplanetary, Blue Origin is betting on infrastructure, building the roads and supply chains that will turn the Moon into an economic hub. Bezos envisions floating factories in space powered by lunar resources, but none of that happens without reliable, routine landings. Blue Moon's success wouldn't just mean another flag on the Moon. It would mean the first gas stations, warehouses, and construction yards beyond Earth, the boring, indispensable scaffolding of a spacefaring civilization. Watching these two visions unfold, SpaceX's interplanetary leapfrog and Blue Origin's step-by-step expansion, is like witnessing the early days of aviation. Some bet on transatlantic flights while others focused on local mail routes. History suggests both were right. The solar system is big enough for giants and freight haulers alike. And when Artemis astronauts finally return to the moon, they might not ride a single spacecraft but an entire ecosystem, one where starships deliver the bold strokes and blue moons handle the fine print. 45 years is a blink in cosmic time, but for two small spacecraft streaking through the void, it's been an entire era of exploration. The Voyager probes, launched in 1977 with less computing power than a modern car key, have outlived every expectation. They've not only crossed the solar system, they've left it entirely, piercing the invisible bubble of the heliosphere to become humanity's first interstellar ambassadors. And right now, as their power dwindles by the year, these time capsules from the disco era are still whispering secrets back to Earth. Voyager's most famous cargo isn't scientific, it's cultural. Mounted on each probe's flank is a golden record, a 12-inch gold-plated copper disc packed with sounds and images meant to tell Earth's story to any civilization that might intercept them. There's Bach concertos and Chuck Berry's Johnny B. Good, greetings in 55 languages, even the brainwaves of a woman falling in love. But these records aren't just artifacts, they're philosophy etched in metal. Carl Sagan's team agonized over every inclusion, from the diagram of DNA to the photograph of a grocery store, snapshots of a species still learning to reach beyond its cradle. The record's instructions, etched in binary, explain how to play them using the cartridge and needle tucked inside. It's a message in a bottle flung into the cosmic ocean with no guarantee it'll ever be found. Yet the Voyager's true legacy lies in their science. Crossing into interstellar space in 2012 Voyager 1 and 2018 Voyager 2, they revealed the heliosphere. The sun's protective magnetic bubble isn't a perfect sphere. It's more like a comet's tail stretched by the galaxy's interstellar wind. Voyager 1 punched through first, its instruments detecting a sudden drop in solar particles and a spike in cosmic rays from deep space. But Voyager 2, taking a different path, found the boundary was porous, with solar plasma leaking out like mist through a screen door. Together, they painted a messier, more dynamic picture of where the sun's influence ends and the galaxy begins. Now, as their power fades, each shutdown is a farewell. In 2019, engineers turned off Voyager 2's cosmic ray instrument heater to conserve energy, knowing it might never warm up again. By 2025, the probes will likely lose the power to run any science instruments at all, becoming silent travelers adrift among the stars. But even in death, they'll teach us. Their final signals, growing fainter with distance, will help calibrate future missions studying the interstellar medium. And their trajectories, Voyager 1 will pass within 1.6 light-years of a star in 40,000 years. Voyager 2 will drift near Sirius in 296,000. These machines were built to explore planets, yet their greatest discovery might be time itself. Every beep from 14 billion miles away is a reminder, space isn't just about distance. It's about endurance. The Voyagers weren't designed to last this long. They just kept going, outliving their creators and transcending their mission. Soon, their voices will fall silent. But their journey, carrying fragments of Earth into the unknown, will continue for eons. Long after our cities have turned to dust, these two golden records will still be sailing, the last echoes of a civilization that dared to reach beyond its sky. Picture a spacecraft so small it fits in your palm, yet so fast it could cross the vast gulf between stars in a human lifetime. That's the radical promise of Breakthrough Starshot, a plan to send thousands of microchip-sized probes to our nearest stellar neighbor, Alpha Centauri, propelled not by rockets but by an Earth-based laser array powerful enough to push them to 20% the speed of light. The concept sounds like pure science fiction, tiny starships, each barely a gram in weight, riding beams of light like cosmic surfboards, but the physics checks out. And if it works, humanity could get its first close-up of an alien solar system before the century's end. The heart of Starshot's design is the light sail, a wafer-thin mirror just atoms thick, stretched over a meter-wide frame. When gigawatt lasers from Earth strike this sail, the photon's momentum transfers to the probe, accelerating it with steady pressure. No fuel tanks, no explosions. Just pure light pushing a speck of humanity across the void. But crafting a sail that won't vaporize under such intense energy is an engineering nightmare. Scientists are testing exotic materials like graphene and ultra-thin metal foams, hunting for something that can reflect 99.9% of the laser's energy while surviving micrometeoroid impacts and interstellar dust. Even a single microscopic hole could destabilize the sail, scattering the laser's focus like a shattered lens. Then there's the data problem. How do you phone home from 4.37 light-years away? Each Starship will carry a femtoscale transmitter, a laser no bigger than a grain of salt powered by a microscopic nuclear battery or a tiny solar cell. Given the distance, the signal reaching Earth will be weaker than a light bulb flickering in a blizzard. Catching it will require a global network of telescopes listening in perfect sync, sifting the cosmic noise for digital whispers. The solution might lie in redundancy, sending thousands of probes so that even if 99% fail, a handful could still relay data. Timing is another hurdle. Alpha Centauri isn't a static target, it's a trio of stars locked in a gravitational dance. The probes, hurtling through at breakneck speed, will have just hours to photograph any planets as they zip past. Their cameras, smaller than a pinhead, must be smart enough to choose targets autonomously, adjusting focus while traveling 40,000 miles per second. Every image captured, every byte of data, will be a snapshot of a world glimpsed in a blink, sent back to Earth on a laser beam that takes 4 years to arrive. The audacity of Starshot forces us to rethink what's possible. Traditional probes like Voyager took decades just to leave our solar system. Starshot's fleet could make the same journey in days. But the project's true legacy might be philosophical. By aiming for the stars with gram-scale probes instead of moon-sized ships, it suggests a future where exploration isn't about brute force, but elegance, where the universe is studied not by conquering giants, but by swarms of intelligent specks, each carrying a fragment of human curiosity into the dark. Critics argue the challenges are insurmountable. The laser array would need to be hundreds of times more powerful than anything built, stretching across miles of desert or space. Even then, a stray cosmic ray could fry a probe's circuits mid-flight. But Starshot's team, backed by luminaries like Stephen Hawking and Mark Zuckerberg, insists these are engineering puzzles, not physical impossibilities. They point to how cell phones shrank from bricks to chips in 30 years, or how CRISPR turned genetic editing from sci-fi to reality. Breakthroughs, they argue, happen fastest when we dare to aim for them. Whether Starshot succeeds or fails, it's already shifted the conversation. For the first time, a mission to another star isn't a distant dream. It's a spreadsheet of technical hurdles waiting to be solved. And if those lasers ever fire, their light won't just propel probes. It'll carry something far more precious, proof that even the universe's vastness is no match for a species that refuses to stay home. Hidden in the vastness of space, countless Earth-like worlds likely orbit distant stars, but spotting them is like trying to find a firefly next to a lighthouse while peering through fog. That's why NASA's proposed LUVOIR telescope could be the game-changer we've been waiting for. Short for the Large Ultraviolet Optical Infrared Surveyor, this behemoth would dwarf even the James Webb Space Telescope, with a primary mirror stretching 15 meters across, nearly 6 times wider than Hubble's. That's enough light-gathering power to not just detect exoplanets, but to photograph them in stunning detail, separating their dim glow from the blinding glare of their host stars like a cosmic coronagraph on steroids. The magic lies in LUVOIR's staggering precision. While Webb studies atmospheres by analyzing how starlight filters through them during transits, LUVOIR aims to cut out the middleman. Its suite of high-tech instruments could directly capture pixels of Earth-sized worlds, mapping continents, tracking weather systems, even detecting biosignatures like oxygen or methane in real time. Imagine staring at an image of Kepler 452b and seeing blue oceans shimmering under a hazy atmosphere, a pale blue dot too. Zero, but this time it's not our own. Key to this vision is LUVOIR's segmented mirror design, an evolution of Webb's hexagonal panels but on a grander scale. 54 adjustable segments would unfold in space, forming a flawless honeycomb capable of observing from ultraviolet to infrared. One proposed instrument, a high-contrast imager called the Planet Formation Camera, could resolve features as small as 200 kilometers across on a planet 10 light-years away, enough to distinguish between clouds and landmasses. Another, an ultra-stable spectrograph, would break down the chemical fingerprints of alien atmospheres with unprecedented accuracy, hunting for molecules like chlorophyll or industrial pollutants that might hint at life or intelligence. Unlike Webb, which orbits the Sun 1,000,000 miles from Earth, LUVOIR would park at Lagrange Point 2 as well, but with a critical upgrade: repairability. Its modular design allows for robotic servicing missions, ensuring decades of cutting-edge observations as technology evolves. Future astronauts or robots could swap out instruments, polish mirrors, or upgrade detectors, a lesson learned from Hubble's longevity and Webb's nail-biting, no fixes allowed gamble. The implications are profound. LUVOIR could survey over 50 potentially habitable exoplanets in its first 5 years, giving us family portraits of worlds where life might thrive. It'd peer into the hearts of galaxy clusters with Hubble's sharpness but Webb's infrared depth, unraveling dark matter's grip on cosmic structures. And in our own solar system, its ultraviolet eyes could track the auroras of gas giants or the volcanic plumes of icy moons in real time. Yet LUVOIR's fate hinges on more than science. It's a political marathon. With an estimated cost rivaling the Apollo program, the project must survive budget cycles and competing priorities. NASA's upcoming astrophysics decadal survey will weigh it against other ambitious concepts like the Habitable Worlds Observatory. But if selected, LUVOIR's launch in the 2030-50s could mark the moment astronomy shifts from studying planets to studying worlds' places, not just points of light. The dream isn't just to find another Earth, it's to look it in the eye. For decades, the International Space Station has been humanity's sole outpost in orbit, a symbol of global cooperation, but also a relic of government-led space exploration. That's about to change. Axiom Space, a Houston-based company, is rewriting the rulebook with a daring plan, attaching sleek, commercial modules to the ISS, then cutting them loose to form the world's first private space station. Picture it like adding a high-tech penthouse to an aging apartment building, then eventually moving that penthouse to its own address in the sky. Axiom's first module, slated to dock with the ISS in 2026, is anything but cramped. Designed with input from Philippe Starck, the legendary French designer behind Virgin Galactic's interiors, its living quarters feature ergonomic furniture, massive Earth-facing windows, and even customizable lighting to combat the disorientation of 16 daily sunrises. But this isn't just a luxury hotel in zero gravity. Nestled between the plush accommodations are cutting-edge research labs where pharmaceutical companies could grow ultra-pure protein crystals for next-gen drugs, and manufacturers might experiment with alloys impossible to forge under Earth's gravity. The station's exterior mounts robotic arms and satellite deployers, turning it into a bustling orbital business park. What sets Axiom apart is its phased approach. By piggybacking on the ISS initially, they avoid the astronomical costs of launching an independent station from scratch. Their modules will tap into the ISS's power and life support for years, while Axiom's engineers learn the rhythms of orbital operations. Then, when the aging ISS is finally retired, likely in 2030, Axiom's modules will detach, firing their own thrusters to become a free-flying destination. This clever strategy turns the ISS's inevitable demise into an opportunity, preserving decades of orbital expertise without missing a beat. The station's dual identity, lab and leisure, reflects a new era in space economics. While NASA and ESA scientists study microgravity's effects on stem cells or artificial retinas, billionaire tourists could be floating next door, sipping espresso brewed in zero-G machines. Axiom's 8-figure tickets, yes, that's tens of millions per seat, include weeks of astronaut training and custom-designed missions. Maybe a tech CEO wants to test prototype robotics, or an artist aims to choreograph the first zero-gravity ballet. There's even talk of sponsoring entire national missions, where countries without space programs can send citizen astronauts to conduct experiments or plant flags. Critics question whether the market exists for such opulent orbital getaways, especially when SpaceX's all-civilian inspiration flights offer shorter, cheaper thrills. But Axiom's early clientele, including a Hollywood director and a former fighter pilot, suggests there's appetite for extended stays. The company's partnerships with SpaceX for crew transport and Collins Aerospace for next-gen spacesuits show they're serious about infrastructure. And with plans to eventually add inflatable habitat modules, Axiom Station could grow to rival the ISS in size, only sleeker, more efficient, and unburdened by 2090s era tech. The station's legacy might lie in its ripple effects. By proving private industry can operate habitats in orbit, Axiom paves the way for everything from orbital film studios to zero-G retirement communities. Their research contracts could accelerate breakthroughs in everything from cancer treatments to fiber optics, making space not just a destination, but a workshop for terrestrial progress. And when those modules finally uncouple from the ISS, it won't just be a technical milestone, it'll be the moment the cosmos truly opens for business. While NASA Mars sample return mission grabs global headlines, China is quietly engineering its own in-game for the Red Planet, one that could rewrite the rules of interplanetary exploration. Tianwen 3 isn't just a mission, it's a statement with a bold plan to retrieve Martian soil by 2030, potentially beating NASA samples home. What makes this rivalry fascinating isn't just the science, it's the stark contrast in approach. Where NASA MSR relies on a complex multi-spacecraft relay, China's playbook is streamlined: 2 launches, no orbital handoffs, and a lander that does it all. The genius or gamble of Tianwen 3 lies in its simplicity. The first launch sends a heavy lander bristling with drills and scoops, designed to collect up to 500 grams of material from Europa Planitia, a basin that may have once been a Martian ocean. Unlike NASA Fetch rover, this lander won't wait for help. It packs its own ascent vehicle, a compact rocket that will blast the samples directly back to Earth without docking in orbit. The second launch, that's the backup, an identical mission heading to a different site, doubling China's odds of success. No interplanetary relay races, no mid-space rendezvous. Just 2 shots at history fired like arrows toward Mars. Technically, it's a masterclass in risk management. By avoiding the Mars orbit rendezvous, a maneuver never before attempted, China sidesteps one of NASA's biggest engineering headaches. Their ascent vehicle doesn't need precision guidance systems to chase down an orbiting mothership. It just needs enough thrust to escape Mars' gravity and curve toward Earth. But there's a trade-off. Direct ascent means carrying more fuel, leaving less room for scientific instruments. NASA Perseverance rover is a rolling laboratory, analyzing samples on site before deciding which are worth sending home. Tianwen-3's lander, it's more like a cosmic vacuum cleaner, gathering material based on pre-programmed criteria without real-time analysis. Geopolitically, this isn't just about rocks, it's about rhythm. China's space agency has perfected a slow but steady cadence, hitting milestones with metronomic precision. Their lunar program, first an orbiter, then a lander, now sample returns, shows a deliberate stair-step approach to dominance. If Tianwen-3 succeeds, it would mark China's third major Mars milestone in a decade, orbiting with Tianwen-1, landing with Tianwen-3, then retrieving samples. Meanwhile, NASA Mars ambitions hinge on intricate collaborations with Europe, where budget debates and shifting priorities can slow progress, the unspoken message. Solo missions might be riskier, but they're also faster when you control every variable. The stakes transcend national pride. Martian samples are cosmic time capsules, and whoever analyzes them first could dictate the narrative of Mars history for decades. Imagine one team announcing evidence of ancient life while another contradicts it, a scenario that could fracture scientific consensus along geopolitical lines. There's also the matter of curation. NASA samples will be quarantined in a biosafety level 4 facility with strict protocols to prevent Earth contamination. China's plans less transparent. If both missions succeed, humanity could suddenly have two competing collections from different Martian eras, each telling a different chapter of the planet's story. Yet collaboration isn't off the table. Some scientists whisper about a détente, a shared repository where samples from both missions are compared side by side. After all, the real enemy isn't rivalry, it's ignorance. Mars doesn't care which flag is on the lander. Its secrets belong to anyone stubborn enough to reach out and grab them. As these two superpowers race toward the same goal, their greatest legacy might not be who gets there first, but how the race itself pushes technology and ambition farther than we ever dreamed. High above our restless planet, two space agencies have teamed up to build something unprecedented, a satellite that sees Earth not just in pictures, but in pulses. NASA and ISRO-NISAR mission, short for NASA-ISRO Synthetic Aperture Radar, isn't your typical climate observer. While most Earth-monitoring satellites snap passive images, NISAR twin radars, one built by NASA, the other by India, fire over 1,800 microwave bursts every second, painting the planet in layers of data no optical camera could capture. This isn't just observation, it's revelation. What makes NISAR revolutionary is its ability to detect movements as subtle as a millimeter, the width of a pencil lead across vast landscapes. Glacial ice creeping toward the sea, NISAR will map its heartbeat. Cities sinking from groundwater depletion, it'll spot the sag before streets crack. Even the silent strain building along fault lines before earthquake surfaces in its data. The satellite's dual-frequency radar L-band from NASA, S-band from ISRO penetrates cloud cover and operates night and day, peeling back layers of vegetation to reveal the ground's hidden shifts. One orbit every 12 days guarantees no corner of the planet escapes its gaze. But NISAR's real power lies in convergence. Its petabytes of data will fuse with climate models like puzzle pieces, showing how melting permafrost in Siberia unleashes methane that then fuels atmospheric warming thousands of miles away. Farmers in drought-stricken regions could receive irrigation alerts based on soil moisture maps updated almost in real time. And for seismologists, the mission offers something tantalizing: patterns. By cataloging microscopic crustal deformations preceding quakes like the slow slip events along the Cascadia subduction zone, scientists might finally crack the code of earthquake forecasting. The collaboration itself is historic. NASA contributes the advanced L-band radar and engineering expertise, while ISRO provides the S-band system and launches the satellite aboard its GSLV Mark Roman II rocket, a marriage of cutting-edge tech and cost-effective execution. Shared ground stations in India and Alaska will ensure near-constant data flow, democratizing access for researchers worldwide. Critics argue such missions risk becoming data fire hoses, overwhelming scientists with information but offering few actionable insights. Yet NISAR AI-driven processing tools aim to turn raw numbers into narratives, highlighting trends human analysts might miss. When paired with ESA's upcoming ROSE-L mission, the two could form a global change detection network, tracking everything from landslide risks to illegal deforestation. The implications stretch beyond science. Insurance companies might adjust premiums based on subsidence maps showing which coastal cities are sinking fastest. Indigenous communities could monitor Arctic ice roads vital for winter supply runs. And for policymakers, NISA's unobscured view of border regions could ease tensions, proving, say, whether water shortages upstream are man-made or climatic. As climate change accelerates, understanding Earth's whispers, the almost imperceptible shifts that precede upheaval becomes existential. NISAR doesn't just observe our planet's transformation. It translates its tremors into a language we might finally understand. The mission's legacy won't be a single eureka moment, but 1,000 small revelations, each one helping humanity navigate a world in flux. Picture a power plant floating in space, no smokestacks, no fuel tanks, just vast mirrors focusing sunlight onto solar panels 24/7, then beaming that energy down to Earth as invisible microwaves. This isn't a sci-fi fantasy. Right now, scientists at Caltech and the European Space Agency are racing to turn this vision into reality, with experiments that could rewrite how we think about clean energy. The premise is simple. Above the atmosphere, sunlight is 10 times more intense, and there's no night or weather to interrupt it. Harvest that untapped potential, and you'd have a near limitless supply of electricity. No fossil fuels, no land-hungry wind farms, just pure energy piped in from orbit. Caltech's Space Solar Power project took its first critical leap in 2023 with the launch of Maple, a palm-sized prototype that successfully wirelessly transmitted solar power in space for the first time. Using an array of flexible, lightweight transmitters, Maple converted sunlight into microwaves and directed them toward receivers a foot away, proving the core tech works in zero gravity. The next step, scaling up dramatically, Caltech envisions kilometer-wide arrays in high orbit, each generating multiple gigawatts, enough to power 1 million homes. The challenges are monstrous. Those microwave beams must stay perfectly focused across thousands of miles to avoid stray energy losses, and the structures need to assemble themselves robotically in space to avoid costly crewed missions. Meanwhile, the European Space Agency's Solaris initiative is tackling the economic elephant in the room. Even with reusable rockets like SpaceX's Starship slashing launch costs, building solar megastations in orbit won't be cheap. Solaris isn't just studying the tech, it's running the numbers, comparing space solar's lifetime costs against terrestrial renewables. Early estimates suggest orbital farms could match ground solar prices by 2040, assuming mass production of lightweight solar cells and constant innovation in wireless power transmission. ESA's researchers are also probing safety concerns. Could a misaligned microwave beam accidentally fry passing aircraft or birds? Their simulations say no. The power density at ground level would be lower than standing in sunlight, with automatic shutoffs if receivers drift off target. Critics argue the idea is a pipe dream, pointing to the staggering scale required. To replace just one coal plant, you'd need solar arrays covering dozens of football fields in space. But proponents counter that space solar's real advantage isn't raw output, it's reliability. While Earth-based renewables suffer cloudy days and seasonal shifts, orbital farms deliver unwavering baseload power, making them perfect partners for intermittent wind and solar. Japan's JAXA agency has already tested microwave power transmission between mountaintops, and China plans a small orbital demonstrator by 2028. The race isn't just about science, it's about claiming the high ground in the next energy revolution. What makes this more than an engineering problem is the geopolitical twist. Whoever masters space solar could dominate global energy markets, with receiver stations deployed anywhere from deserts to offshore platforms. Imagine a world where countries no longer fight over oil fields, but over orbital slots in geostationary orbit. The tech could also be a lifeline for disaster zones. Drop a receiver in a hurricane-ravaged region, and instant power flows from space. The dream hangs on a delicate balance. Push too fast and the costs could bankrupt early adopters. Move too slow and climate change might outpace us. But one thing's certain, the era of staring up at the sun and wondering what we're missing is ending. The future isn't just green, it's orbital. After 7 years in space and a historic touchdown on asteroid Bennu, NASA OSIRIS-REx spacecraft isn't ready for retirement. It's gearing up for an encore that could redefine how we protect Earth from cosmic threats. Renamed OSIRIS-APEX for its next act, the probe is now racing toward a new target. Apophis, the so-called God of Chaos asteroid, set to skim shockingly close to our planet in 2029. This isn't just another flyby. At a mere 19,000 miles, Apophis will pass closer than some weather satellites, giving half the world's population a front-row seat to a celestial near-miss. An OSIRIS-APEX will be there, not just to watch, but to study how Earth's gravity reshapes the asteroid in real time, a planetary defense experiment no lab could ever replicate. Apophis itself is a time capsule from the solar system's violent infancy. Roughly the size of 3 football fields, this rubble pile asteroid spins like a slow-motion bullet, its surface littered with boulders and dust that could hold clues to how planets first assembled. But what truly fascinates scientists is its brush with Earth's gravity in April 2029. As Apophis grazes our planet, tidal forces will stretch and torque its structure, potentially triggering landslides or even exposing fresh material beneath its weathered surface. OSIRIS-APEX, arriving in orbit shortly after this cosmic tango, will become the ultimate witness, mapping every crack and crevasse with its suite of cameras, spectrometers, and laser altimeters. The mission's repurposed tools tell a story of adaptability. Originally designed to pluck samples from Bennu's surface, OSIRIS-APEX robotic arm won't be collecting rocks this time. Instead, it'll serve as a makeshift thruster. By hovering just meters above Apophis and firing its nitrogen gas jets, the spacecraft will blast the asteroid's surface, kicking up debris to reveal what lies beneath. It's an ingenious hack, turning sample collection hardware into a planetary defense probe. Meanwhile, the spacecraft's thermal emission spectrometer will monitor how sunlight heats and fractures Apophis's surface over time, data critical for predicting how similar asteroids might behave if deflected away from Earth. The stakes couldn't be higher. While Apophis itself poses no impact risk for at least a century, its close approach offers a once-in-a-thousand-year opportunity to stress-test our planetary defense systems. Radar observatories worldwide will track its trajectory with millimeter precision, while OSIRIS-APEX close-up data will refine models of how asteroids respond to gravitational nudges, knowledge that could prove vital if we ever need to divert a real threat. There's poetic symmetry here. The spacecraft that once brought us pieces of Bennu, our solar system's ancient building blocks, now stands guard against those same materials' destructive potential. Yet the mission's legacy might hinge on surprises. When OSIRIS-REx touched Bennu, scientists were stunned to find the surface so porous it barely resisted the probe's touch, like plunging into a ball pit. Apophis could harbor similar revelations. Will Earth's gravity shake loose unexpected avalanches? Could hidden voids beneath its surface amplify quakes from tidal forces? Every answer OSIRIS-APEX beams back will sharpen our understanding of these cosmic wanderers, not just as scientific curiosities but as potential hazards. By the time the spacecraft's cameras capture Apophis receding into the darkness, we won't just have studied an asteroid. we'll have taken humanity's first concrete steps toward mastering the delicate art of celestial threat assessment, proving that sometimes the best defense is a really good close-up. Mars won't be conquered by flags and footprints. It'll be built, brick, by crews who arrive not to visit but to stay. The blueprints for humanity's first off-world colony are already taking shape, and they reveal two radically different visions of what a Martian home could be. On one side, SpaceX dreams of geodesic domes towering over the rust-colored plains, their translucent panels flooding interiors with sunlight filtered to block harmful radiation. These wouldn't be cramped metal cans, they'd be high-ceilinged spaces filled with hydroponic gardens and communal areas, their aluminum frames wrapped in a skin of solar cells and insulated by layers of locally sourced Martian regolith. Elon Musk envisions entire cities under these domes, their pressure-tested airlocks leading to networks of tunnels where colonists could escape dust storms or solar flares. NASA approach ditches the glass for pragmatism. Their 3D printed habitats, developed through years of competitions like the 3D Printed Habitat Challenge, look more like giant igloos made of compressed Martian soil. Robotic rovers would gather iron oxide-rich regolith, mix it with binding polymers, then layer it into domes using massive printers. Think pottery wheels scaled up for alien construction. The result, structures with walls thick enough to block cosmic rays, their curved shapes naturally distributing stress from internal pressure. Inside, inflatable modules shipped from Earth would unfold like high-tech balloons, creating livable spaces lined with radiation-absorbing water tanks and flexible solar panels. The genius here is minimalism. Instead of hauling entire buildings across space, you transport a printer and let Mars provide the bricks. Both concepts share one non-negotiable: radiation shielding. Mars lacks Earth's magnetic field and thick atmosphere, leaving colonists exposed to galactic cosmic rays capable of damaging DNA. SpaceX's solution leans on transparency. Their glass would likely be laminated with layers of polyethylene, a hydrogen-rich material that excels at scattering radiation, while water-filled ceilings act as additional barriers. NASA compacted regolith walls achieve similar protection through sheer mass, just 3 feet of Martian dirt blocks over 90% of harmful particles. Some designs even propose lining habitats with slabs of lithium hydride, a lightweight compound that gobbles up neutrons like cosmic Pac-Man. But the real game changer is ISRU, in situ resource utilization, the art of living off the land. Every ounce saved by using local materials means more room for critical supplies. Martian soil isn't just potential concrete. Electrolysis units could extract oxygen locked in its minerals, while drills might tap underground ice for drinking water and hydrogen fuel. The thin atmosphere, mostly carbon dioxide, offers another treasure: MOXIE, a toaster-sized device already tested by NASA. Perseverance rover proves we can split CO2 into breathable oxygen and carbon monoxide propellant. Future bases could scale this up, turning the very air into life support and rocket fuel. The psychological blueprint matters as much as the engineering. Isolation studies in Antarctica and underwater labs like Aquarius prove that cramped quarters breed tension. That's why NASA HERA program simulates year-long missions in a Houston warehouse, studying how crews cope with delayed communications and recycled air. SpaceX's glass domes aim to counter claustrophobia with panoramic views of Martian sunsets, while vertical farms double as green sanctuaries. Both designs prioritize communal kitchens and workspaces because on Mars, your roommate isn't just a coworker, they're your lifeline. What unites these visions is scalability. Early bases might house a dozen scientists, but the goal is villages, then cities. NASA 3D printers could churn out emergency shelters for expanding settlements, while SpaceX's dome kits might arrive in cargo starships pre-assembled, popping open like high-tech umbrellas. The ultimate test won't be surviving the first year, it's designing spaces where children can grow up thinking of Mars not as a frontier, but as home. And when those first Martian architects break ground, their blueprints won't just shelter bodies. They'll shape the culture of an entirely new branch of humanity. While most telescopes hunt for exoplanets one at a time, Europe's PLATO mission is about to turn planet spotting into an industrial-scale operation. Slated for launch in 2026, this space observatory doesn't have just one or two cameras. It boasts 26 identical telescopes packed onto a single spacecraft platform, creating a honeycomb of eyes scanning the cosmos simultaneously. Unlike Kepler's fixed gaze on distant stars or TESS patchwork survey of bright nearby systems, PLATO's strategy is surgical precision on steroids. Its targets G-type stars nearly identical to our Sun, where planets in the habitable zone could harbor conditions ripe for life as we know it. Each of PLATO cameras functions like a super-sensitive light meter, capable of detecting dips in stellar brightness smaller than 1 part in 10,000. The equivalent of spotting a fly passing in front of a car headlight from miles away. But what makes this mission revolutionary isn't just sensitivity, it's endurance. PLATO will monitor each star field for up to 2 years straight, catching multiple transits of the same planet to confirm orbits and rule out false positives from stellar flares or dust clouds. That extended stare allows something unprecedented, measuring tiny variations in starlight caused by seismic waves rippling through a star's interior. These astroseismology readings act like cosmic fingerprints, revealing a star's exact age, mass, and composition, critical data for determining whether any orbiting planets are truly Earth-like or just barren rocks. The telescope's design borders on obsessive optimization. Its cameras operate in 2 groups: 24 normal telescopes with a wide 25-degree field of view for hunting planets, plus 2 fast telescopes that capture brightness changes every 2.5 seconds to study stellar pulsations. This dual-mode operation turns PLATO into both a planet-finding machine and a stellar physics lab. Even its orbit is calculated for perfection, stationed at Lagrange point 2, the same quiet vantage as JWST, but angled slightly off-center to avoid light pollution from the Moon and Earth. Where Kepler gave us statistics and TESS delivered nearby targets, PLATO aims for gold standard characterization. Among its 1,000 confirmed planets, scientists expect to find dozens of rocky worlds with orbits placing them firmly in the Goldilocks zone, not too hot, not too cold. But the real jackpot, systems like ours. While most known exoplanetary systems are crammed with worlds hugging their stars closer than Mercury orbits the Sun, PLATO's sensitivity to longer orbital periods means it could finally answer whether Solar System 2 zeros are common or cosmic flukes. The mission's legacy might lie in its selection of follow-up targets. Every Earth-sized candidate PLATO discovers will get scrutinized by JWST and the upcoming extremely large telescope, their atmospheres probed for biosignatures like oxygen or methane. It's the difference between knowing a planet exists and understanding whether it breathes. By the time PLATO's 6-year primary mission ends, we won't just have a catalogue of exoplanets, we'll have a shortlist of worlds where the chemistry of life might already be underway. Deep in the permanently shadowed craters of the Moon's south pole, where temperatures plummet to -400 degrees Fahrenheit, a treasure trove of water ice hides untouched by sunlight for billions of years. NASA's Viper rover isn't just another lunar explorer. It's a prospector on a critical hunt, mapping these frozen reserves with the precision of a cosmic cartographer. Slated to land in late 2024, this golf cart-sized robot will spend 100 days traversing the treacherous terrain near Nobile Crater, its 4-wheel drive system navigating slopes as steep as 15 degrees while its drill plunges up to 3 feet into the lunar dirt. Every scoop could rewrite the economics of space exploration, because water isn't just for drinking, it's the oil of the new space age, capable of being split into hydrogen for rocket fuel and oxygen for breathing, turning the Moon into a cosmic gas station for missions bound deeper into the solar system. What sets Viper apart is its real-time adaptability. Unlike rovers that follow pre-programmed paths, Viper AI-driven navigation system, dubbed Survival Mode, constantly assesses terrain hazards, rerouting on the fly to avoid deadly quicks and like regolith traps. Its headlights, the first ever on a lunar rover, will pierce the abyssal darkness of these craters, illuminating landscapes no human or machine has ever seen. But the true magic lies in its trio of spectrometers. The NERVs and M-SOLO instruments will analyze the chemistry of drilled samples, distinguishing between water ice and mere hydrogen signatures, while the neutron spectrometer system peers beneath the surface, mapping ice deposits up to 3 feet deep like an X-ray scanner for frozen gold. The mission's timing is no accident. Viper findings will directly inform NASA Artemis program, pinpointing landing zones where astronauts can harvest ice with minimal effort. Early data could determine whether future crews deploy solar-powered ice miners or microwave extraction units that vaporize soil to capture escaping water vapor. There's even talk of Viper-style robots being repurposed as autonomous drilling rigs, maintaining ice harvesting operations before humans arrive, yet the challenges are formidable. Lunar regolith is notoriously abrasive, like crushed glass capable of clogging machinery and shredding seals. Viper drill bit is crafted from tungsten carbide, a material tough enough to handle the grind, while its heat-resistant electronics are tucked inside a thermally controlled, warm box to survive temperature swings of 500 degrees between sunlight and shadow. Power comes from a novel hybrid system: solar panels during the 2-week lunar days, batteries during the long nights, and strategic naps to conserve energy during extreme cold. Beyond practicality, Viper carries profound scientific stakes. The ice it samples might be older than Earth's oceans, a frozen archive of comet deliveries and solar wind interactions dating back to the solar system's infancy. If isotopic ratios in the water match those found on Earth, it could bolster theories that our planet's oceans were seeded by ancient lunar ice bombardments. Alternatively, completely different ratios might rewrite the story of how water arrived in the inner solar system. The rover won't be working alone. Its landing site will be scouted in advance by NASA, a lunar trailblazer orbiter, creating high-resolution maps of surface temperatures and water signatures. Meanwhile, Viper data will sync with India's upcoming Pratham rover mission, creating the first multi-robot survey of lunar volatiles. This isn't just exploration, it's the dawn of extraterrestrial resource management. When Viper mission ends, its legacy will live on in the blueprints of lunar bases yet to be built. Every ice patch it catalogs could become a future landing pad, every drill sample a clue to the moon's chaotic past. And for the astronauts who eventually follow its tracks, Viper's greatest gift won't be the maps it leaves behind, but the certainty that when they arrive, the essentials of survival, air, water, even rocket fuel, will already be waiting. Imagine pointing a telescope at a distant star and not just detecting a planet but seeing its oceans shimmer, its clouds drift, even its continents basking in the sunlight of another sun. That's the staggering promise of NASA's proposed Habitable Worlds Observatory, a space telescope so advanced it could transform exoplanet science from guesswork into geography. Slated for possible launch in the 2040s, this observatory isn't just another instrument, it's a philosophical leap designed to do what no telescope has done before: directly image dozens of Earth-like worlds and analyze their atmospheres for signs of life. Where James Webb studies planetary shadows and TESS hunts for transits, HWO aims to capture family portraits of alien solar systems, turning pixels of light into portraits of places we might one day call home. The technology behind HWO reads like a sci-fi wishlist. At its heart lies a coronagraph so precise it can block out a star's light 10 billion times brighter than its orbiting planets, like trying to spot a firefly next to a lighthouse while squinting through fog. But unlike Hubble's static coronagraph, HWO's will be adaptive, using deformable mirrors that tweak their shape 1,000 times per second to cancel starlight with nanometer precision. Pair that with a mirror likely stretching 6 to 15 meters across. Some concepts even suggest segmented designs inspired by JWST. And you've got a light-gathering power capable of resolving planets just 10 million miles from their stars, snug in the habitable zone where liquid water could pool. HWO didn't emerge from nowhere. It's the culmination of decades of lessons from projects like LUVOIR and HAB-X, two earlier concepts that laid the groundwork. LUVOIR, with its 15-meter mirror and ultraviolet to infrared range, was the Swiss Army knife of telescopes equally adept at studying exoplanets and distant galaxies. HAB-X took a different tack, favoring a smaller 4-meter mirror but pairing it with a massive starshade flying 40,000 miles away to block starlight. HWO splits the difference, borrowing LUVOIR high-resolution spectroscopy for atmospheric analysis while adopting HAB-X's emphasis on contrast ratios. The result, a mission laser focused on one question: which of these worlds could host life? But HWO's real genius might be its modularity. Unlike JWST, which launched as a finished masterpiece, this observatory is designed for upgrades. Imagine docking ports for future instruments, or even robotic missions that could replace aging components. A telescope that evolves as technology improves. Early designs suggest it'll park at Lagrange Point 2, that gravitational sweet spot 1,000,000 miles from Earth, but with one critical improvement over JWST: serviceability. Whether via astronauts or robots, HWO could be maintained, ensuring its mission spans decades rather than years. The scientific payoff would rewrite textbooks. HWO could identify pale blue dots by analyzing their reflected light for ocean glint, sunlight bouncing off liquid surfaces at characteristic angles. Its spectrographs would hunt for atmospheric gases like oxygen, methane, or even industrial pollutants, distinguishing between Earth-like biospheres and exotic chemistries. And if it finds a world with seasons' subtle shifts in surface color over time, we might witness alien springtimes unfolding across light years. Yet the telescope's legacy might be more profound than data. By rendering distant worlds as tangible places, not just specks in a graph, HWO could collapse the psychological distance between stars. A child born today might grow up with posters of Proxima Centauri B's jagged coastlines or TRAPPIST-1E's sprawling deserts on their bedroom wall. The universe would feel not just vast but visitable, and when that first unmistakable biosignature appears in HWO's data, humanity will face a realization as thrilling as it is humbling. We're not just explorers of the cosmos. We're neighbors. While Earth-based detectors like LIGO have revolutionized our understanding of gravitational waves, ripples in space-time from colliding black holes and neutron stars, they're fundamentally limited by our planet's noise. Seismic tremors, passing trucks, even ocean waves create vibrations that drown out the universe's faintest whispers. That's why the Laser Interferometer Space Antenna, or LISA, isn't just an upgrade, it's a paradigm shift. Slated for launch in the 2030s, this trio of spacecraft will form a gravitational wave observatory with arms 2.5 million kilometers long, floating in the pristine quiet of space where the only background noise is the universe itself. LISA design is breathtaking in its precision. 3 identical spacecraft will trail Earth in a triangular formation, each separated by those staggering millions of kilometers. Inside each one, floating test masses made of gold-platinum alloy will hang in near-perfect freefall, shielded from solar wind and cosmic rays by the spacecraft around them. Laser beams constantly measure the distances between these masses, and here's the magic part: when a gravitational wave passes through, it will stretch and squeeze space-time itself, shifting those distances by less than the width of a single atom. LISA lasers can detect changes that small across distances wider than the Sun. What makes this mission revolutionary isn't just sensitivity, it's the frequency range it unlocks. Earth-based detectors like LIGO catch high-frequency waves from stellar mass black holes merging in seconds, but LISA will tune into the universe's base notes, the slow, monstrous ripples from supermassive black holes spiraling together over years. These behemoths, millions to billions of times the Sun's mass, lurk at the hearts of galaxies, and their collisions shake the cosmos like timpani drums. LISA could catch pairs orbiting each other decades before they merge, offering a front-row seat to the buildup of spacetime's most violent events. The scientific payoff spans astrophysics. By tracking how gravitational waves warp their path around galaxies, LISA could map dark matter's distribution in 3D. It might spot the gravitational wave background, the faint hum from countless mergers across cosmic time, or even exotic objects like cosmic strings, hypothetical defects in spacetime left over from the Big Bang. And if black holes really do ring after merging, as Einstein's equations predict, LISA-long observations could measure their tones with the precision of a tuning fork, testing general relativity like never before. Yet LISA's true legacy might be unexpected discoveries. Gravitational wave astronomy is barely a decade old. Every new detector has revealed surprises, from black holes of impossible sizes to neutron star collisions forging gold. In the silent dark between planets, LISA won't just listen to the universe. It might hear something no one even thought to predict. Most spacecraft missions measure their lifespans in years, maybe decades if they're lucky. But what if we dared to think in centuries? That's the radical premise behind the Johns Hopkins Applied Physics Lab's Interstellar probe, a mission not just designed to leave our solar system, but to keep functioning for 1,000 years as it journeys into the interstellar void. This isn't about quick flybys or temporary data collection. It's about planting humanity's flag in the cosmic ocean and keeping it there for generations untold. The numbers alone stagger the imagination. 1,000 astronomical units, that's the probe's minimum target distance, roughly 30 times farther than Pluto. At that range, the Sun would appear as just another bright star, its light taking nearly 6 days to reach the spacecraft, but the real ambition lies in the timeline. A millennium-long mission means this probe must outlast civilizations, surviving long enough to witness technological revolutions we can't yet conceive. Engineers aren't just building hardware, they're crafting a time capsule that can adapt, communicate, and endure across epochs. Propulsion is the first make-or-break challenge. Chemical rockets are out, they lack the efficiency for such marathon journeys. Solar sails, too fragile over centuries of micrometeoroid bombardment. The current frontrunner is a nuclear electric propulsion system where a compact reactor heats liquid hydrogen to blistering temperatures, shooting it out the nozzle at speeds chemical engines can't match. But even this cutting-edge tech needs upgrades. The probe might carry a radioisotope rejuvenation system, banks of plutonium pellets that robots could swap into decaying power units centuries from now, like changing batteries in a flashlight built by your great-great-grandparents. Then there's the interstellar medium itself, the thin soup of gas and dust between stars. Unlike Voyager's crude measurements from the solar system's edge, this probe would carry quantum sensors capable of mapping magnetic fields atom by atom, detecting the subtle pressure of starlight pushing against the craft, even sampling dust grains originating from ancient supernova. Some instruments would focus on stellar weather, how shockwaves from dying stars ripple through the galaxy, potentially influencing planetary climates light years away. Communication across such distances defies current technology. A laser-based system is the leading candidate, with Earth-based receivers the size of football fields catching faint optical signals. But the team is also exploring data pods, small backup capsules ejected periodically toward Earth, each carrying decades' worth of measurements in hardened diamond-like storage. Even if the main probe fails, these cosmic message bottles could keep the mission alive. what makes this endeavor extraordinary isn't just the engineering. It's the philosophy. A 1,000-year mission forces us to confront our species' short attention span. The team is already designing AI capable of reinterpreting its own mission parameters as science evolves, and discussing how to embed repair instructions in formats future civilizations could decode. This probe wouldn't just be a machine, it would be a covenant, a promise that humanity's curiosity can outlast the pyramids, the Great Walls, even the languages we speak today. When it finally falls silent, whether in 2300 or 3000 AD, its last transmission won't just be data. It'll be proof that we dreamed big enough to reach beyond our own lifespan, toward a future we'll never see but dared to imagine. Imagine a ribbon stretching from the moon's surface all the way back to Earth, not a fantasy, but a real proposal that could turn interplanetary logistics on its head. The Liftport Group's lunar space elevator concept is one of those ideas that sounds like pure science fiction until you crunch the numbers. The principle is simple: a cable anchored to the moon's surface, extending through Lagrange point 1, a gravitational sweet spot where Earth's and the moon's pulls balance out down to a counterweight in high Earth orbit. Cargo climbers powered by solar energy would inch their way up and down this cosmic highway, slashing the cost of transporting materials between worlds by avoiding the fuel-guzzling tyranny of rocket launches. The real showstopper here is the material. Earth-based space elevators have long been stymied by the need for a cable stronger than any known substance, something that can withstand the crushing tension over thousands of miles without snapping. But the moon's weaker gravity changes the game. A lunar tether could theoretically be built with existing carbon nanotubes, which are already 50 times stronger than steel at a fraction of the weight. The catch: we've never manufactured nanotubes at the required scale. Think hundreds of thousands of miles of flawless, defect-free strands. Current production methods max out at centimeter lengths, and even those often contain microscopic weak points. Liftport's roadmap hinges on breakthroughs in automated nanotube weaving, possibly using orbital factories where zero gravity could help align fibers with atomic precision. Japan's 2050 vision adds another layer of intrigue. Their aerospace exploration agency has mapped out a phased approach, starting with robotic missions to test tether deployment in low Earth orbit, then scaling up to a lunar demonstrator by 2040. One proposal involves a breadcrumb strategy, sending a series of climbers that leave reinforced segments of cable behind them, slowly building the structure like ants constructing a bridge. Early models suggest a functioning lunar elevator could transport payloads for as little as $500 per pound, compared to the tens of thousands it costs to launch the same weight on rockets. But the challenges go beyond materials science. A lunar tether would face constant micrometeoroid bombardment, solar radiation degrading its polymers, and electrostatic charging from the moon's dusty plasma environment. Engineers are exploring self-healing coatings laced with liquid metal alloys that could seal punctures autonomously, while embedded sensors would monitor stress fractures in real time. Then there's the dance of orbital mechanics, keeping the Earth side counterweight stable as our planet's rotation subtly tugs on the system. Some designs propose an active stabilization system using ion thrusters or even solar sails to maintain tension. The geopolitical implications are equally fascinating. Whoever builds the first functional space elevator could effectively control the bottleneck of lunar commerce, sparking debates over whether it should be a multinational consortium or a privatized toll road. Legal frameworks don't yet exist for off-world infrastructure of this scale. Imagine the complexities of maintaining a structure that passes through multiple orbital regimes and jurisdictions. Yet the potential rewards are astronomical. A lunar elevator could open the floodgates for helium-3 mining, off-world manufacturing, even tourism. Picture solar panels manufactured on the moon's airless plains, then shipped down the tether to power Earth's grids, or lunar water ice being transported to orbital depots as rocket fuel for Mars missions. It's not just about getting stuff off the moon, it's about turning our celestial neighbor into the galaxy's first interplanetary shipping hub, the most poetic part. Unlike Earth-bound elevators that would take decades to recoup their costs, a lunar version could pay for itself relatively quickly by enabling the very industries that would expand its use. Every kilogram of lunar regolith processed into oxygen or metals, every solar satellite assembled from moon-mined materials would make the next kilogram cheaper to transport. It's a classic bootstrap scenario where the infrastructure enables the economy that funds the infrastructure. Skeptics argue the engineering hurdles are insurmountable with current tech, and they're not wrong. But remember, the internet, the airplane, even the humble light bulb all seemed impossible until they weren't. The lunar elevator isn't just a transportation project. It's a test of our patience, our ingenuity, and our willingness to invest in a future where Earth and the moon aren't just neighbors, but partners in a cosmic supply chain. And if the tether ever does unfurl, shimmering in the sunlight like a spider's silk stretching across the void, it won't just be a marvel of engineering. It'll be a monument to the audacity of thinking big, really, really big. When ingenuity first spun its carbon fiber blades in Mars' thin atmosphere, it wasn't just a technical marvel, it was a revelation. That tiny helicopter, designed as a proof of concept, ended up completing over 50 flights, outlasting its planned mission by years and transforming how scientists explore the red planet. Now NASA Mars Helicopter 2.0 is poised to take that legacy even further. This isn't just an upgrade, it's a full evolution, engineered to carry heavier payloads, scout terrain for human missions, and even serve as a robotic partner for future astronauts. The new rotorcraft, roughly twice the size of Ingenuity, trades its predecessor's experimental status for real utility. While Ingenuity weighed in at a mere 4 pounds, this next-gen model boasts a 10-pound frame, enabling it to lug cameras, spectrometers, and even small sample containers. Its dual rotors, spanning over 4 feet tip to tip, are crafted from ultra-lightweight composites reinforced with titanium, a necessity for slicing through an atmosphere just 1% as dense as Earth. But the real breakthrough lies in its autonomy. Unlike Ingenuity, which relied on pre-programmed flight paths, Helicopter 2.0 will feature AI-driven navigation capable of recalculating routes in real time to avoid hazards like dust devils or jagged rock formations. Scouting will be its primary mission. Imagine a team of astronauts prepping to traverse Mars' Jezero crater. Before they risk their rover in treacherous sand traps or steep ravines, the helicopter could zip ahead, mapping safe routes with LiDAR and high-resolution cameras. It might even pinpoint deposits of water ice or mineral resources, transmitting 3D terrain models to handheld devices worn by explorers and in emergencies. These rotorcraft could act as couriers, ferrying spare parts or medical supplies between base camps faster than any rover. The science potential is equally staggering. Equipped with ground-penetrating radar, Helicopter 2.0 could uncover ancient river channels buried beneath the surface, clues to Mars' watery past. Its infrared spectrometer might detect subtle heat signatures from geothermal vents, hinting at underground reservoirs. And with the ability to hover just feet above the ground, it could inspect intriguing rock formations up close, guiding rovers like Perseverance to the most promising samples. Yet the challenges are daunting. Mars' cold nights dipping to -130 degrees Fahrenheit can brittle even the toughest materials. Engineers have incorporated self-heating components and redundant power systems to keep critical systems humming. Dust accumulation, which nearly doomed Ingenuity during a global storm, is mitigated by hydrophobic coatings that repel fine particles. And because human missions will demand reliability, The design includes swappable modular components, allowing astronauts to perform field repairs with simple tools. What makes this mission pivotal isn't just the tech, it's the paradigm shift. Ingenuity proved flight on Mars was possible. Helicopter 2.0 proves it's indispensable. Future colonies might deploy entire fleets of these aerial scouts, buzzing across the rust-colored landscape like mechanical dragonflies, transforming how we navigate and understand an alien world. And when the first humans finally step onto Mars, they won't just be explorers. They'll be commanders of a hybrid expedition, part rover, part rotorcraft, unlocking the planet's secrets from the ground and the sky. Buried beneath the rust-colored dust of Mars, secrets from billions of years ago might be waiting, fragile traces of organic molecules that could rewrite the story of life in the cosmos. That's the gamble behind the Mars Rosalind Franklin rover, a mission so audacious it was designed to drill 2 meters into the Martian surface, deeper than any probe has ever reached. But this isn't just a story of scientific ambition, it's a tale of geopolitical whiplash, technical grit, and a rover that spent years in storage, waiting for its chance to make history. Originally a collaboration between the European Space Agency and Russia's Roscosmos, the Rosalind Franklin rover was built to answer a question that's haunted scientists for decades. If life ever flickered into existence on Mars, where would its fingerprints hide? The surface is a radiation-blasted wasteland, but drill deep enough below where cosmic rays and ultraviolet light can penetrate, and you might find a time capsule of ancient chemistry. The rover's namesake, chemist Rosalind Franklin, famously helped uncover DNA's structure, and her robotic counterpart carries tools fit for a molecular detective. Its onboard lab, the Mars Organic Molecule Analyzer, can vaporize soil samples and sort the resulting gases atom by atom, hunting for the telltale patterns of amino acids or lipids, building blocks of life as we know it. But in 2022, the mission hit a wall not of rock but of politics. Russia's invasion of Ukraine forced ESA to sever ties with Roscosmos, leaving the rover grounded indefinitely. The fallout was brutal. Russia had provided the landing platform, the rockets, even the radioisotope heaters to keep the rover alive during frigid Martian nights. Overnight, a decade of planning unraveled. The rover, already packed and ready for launch, was mothballed in an Italian clean room while engineers scrambled to redesign an entire mission on the fly. Now ESA is rewriting the playbook. The new plan: replace Russia's landing system with a European-made alternative, possibly borrowing tech from NASA, a Mars sample return mission. The rovers drill a marvel of engineering with a corkscrew-like design that can retrieve pristine cores without contamination, has been retested bolt by bolt. And the launch, once scheduled for 2022, is now tentatively set for 2028, with a fresh rocket, likely an Ariane 6, booked for the job. The delay is agonizing, but it might come with a silver lining. The extra time has allowed engineers to upgrade the rover's autonomy, letting it navigate treacherous terrain without constant earthly oversight. New spectral cameras, fine-tuned during the hiatus, can now distinguish between minerals formed in water versus volcanic activity, a subtlety that could pinpoint the most promising drill sites. And lessons from NASA Perseverance, which has been caching samples nearby in Jezero crater, could help Rosalind Franklin prioritize its own targets. Yet the mission's biggest challenge remains untested, that record-breaking drill. Martian soil at 2 meters down is a mystery. It could be brittle as chalk or stubborn as concrete. The drill's rotating and percussive action is designed to handle both, but if it jams or snaps, there's no repair crew on Mars to fix it. Every gram of retrieved material will pass through an ultra-clean sealing system to prevent earthly contamination, because the stakes are just that high. Finding even a single strand of complex organics wouldn't prove life existed, but it would scream that Mars was once a place where life could have thrived. The Rosalind Franklin rover is more than a machine. It's a symbol of resilience, of science pushing forward even when politics tries to pull it back. And if it someday rolls across Planum, its drill biting into soil untouched for eons, it won't just be exploring Mars. It'll be proving that curiosity, once kindled, can survive even the longest delays. The universe's secrets aren't going anywhere, and neither are we. As lunar ambitions shift from flags and footprints to mining contracts and tourist hotels, an unexpected player is stepping onto the cosmic stage, the United States Space Force. Their proposed cislunar highway patrol isn't about laser battles or orbital fortresses. It's a traffic cop for the next gold rush, designed to monitor the quarter-million-mile expanse between Earth and the Moon as it becomes the solar system's busiest shipping lane. With dozens of nations and private companies plotting missions, from NASA Artemis landings to Luxembourg-based startups eyeing helium-3 extraction, the chaos potential is staggering. Picture this: a derelict mining tug drifting into the path of a crude lunar ferry, or rival companies jostling over prime real estate near the Moon's water-rich poles. The highway patrol's mandate: prevent crashes, track debris, and keep the peace in a realm where the nearest police station is 240,000 miles away. The operational blueprint reads like sci-fi meets air traffic control. A network of sensor satellites would park at Lagrange points, gravitational eddies where Earth and Moon's pulls balance out, acting as celestial watchtowers. Equipped with infrared scanners and radar, they'd catalog everything from SpaceX's Starship tankers to China's robotic sample return probes, plotting trajectories with military-grade precision. Machine learning algorithms would flag anomalies, a satellite mysteriously changing orbit, or a cloud of debris bursting from a failed lander. Early prototypes already exist. The Space Force's tiny SB-13 satellite recently demonstrated long-range cislunar tracking, spotting objects farther than any previous system. But scaling up means solving cosmic-scale problems. How do you enforce right-of-way rules when radio signals take seconds to reach the Moon? Who determines if a drifting fuel depot is abandoned property or salvage? Critics hear echoes of colonial history in the patrol's creation, warning that militarizing cislunar space risks turning cooperation into confrontation. The Outer Space Treaty of 1967 bans weapons of mass destruction in orbit but says little about patrol craft or surveillance networks. China and Russia have accused the U.S. of using debris concerns as a pretext for dominance, while astrophysicists fret that military satellites could interfere with delicate radio telescopes in the Moon's quiet far side. Even allies question the optics. The European Space Agency prefers civilian-led tracking, arguing that transparency builds trust better than armed monitoring. Yet the need for some oversight is undeniable. Lunar orbits are cluttered graveyards of Cold War relics. NASA estimates over 50 derelict objects already loop the Moon, from Soviet lunar probes to Apollo-era boosters. Add thousands of new missions, and the risk of catastrophic collisions skyrockets. A single screw traveling at orbital speeds could puncture a habitat or sever a tether cable, triggering a chain reaction of debris. The Highway Patrol's proponents argue it's not about control, but sustainability, preventing a Kessler syndrome scenario where the Moon becomes encircled by a shroud of shrapnel, cutting off access for generations. The program's ultimate test may be balancing dual identities, part referee, part scout. Beyond tracking hazards, its sensors could map lunar ice deposits or scout safe landing zones, sharing data with civilian agencies. Early proposals even suggest embedding civilian observers in its command chain, ensuring military capabilities serve scientific and commercial needs. It's a tightrope walk. One misstep could alienate the very nations and companies it aims to protect. But if it succeeds, the Cislunar Highway Patrol might redefine how humanity shares the frontier, proving that beyond Earth's atmosphere, security doesn't have to mean secrecy. The goal isn't to weaponize the moon, it's to keep it open for business. While most of our data travels through cables and radio waves, vulnerable to hackers and cosmic interference, scientists are pioneering an entirely new kind of internet, one woven from the bizarre laws of quantum physics. China's Misha satellite, launched in 2016, proved it's possible to create theoretically unhackable communication channels spanning continents, using photons so delicate that any attempt to intercept them would immediately alert both sender and receiver. Now, that same quantum technology is being adapted for deep space, potentially enabling colonies on Mars or the Moon to communicate with Earth across millions of miles without fear of eavesdropping or sabotage. The magic lies in quantum key distribution, or QKD. Unlike traditional encryption, where hackers can copy data and crack codes given enough time, quantum systems exploit a fundamental quirk of nature. Observing a quantum particle irrevocably changes its state. Misha demonstrated this by firing pairs of entangled photons particles mysteriously linked across any distance to ground stations over 700 miles apart. When one photon was measured, its twin instantly assumed a corresponding state, generating identical encryption keys at both locations. Any spy trying to intercept those keys would disrupt their quantum signatures like a burglar leaving footprints in fresh snow. But scaling this to interplanetary distances means tackling problems Earth-bound systems never face. Photons traveling through space must contend with atmospheric turbulence, cosmic rays, and the mind-bending challenge of aligning telescopes across moving planets. NASA proposed Deep Space Quantum Link would use ultra-stable lasers and adaptive optics to compensate, with satellites acting as cosmic relay stations. One concept envisions a constellation of quantum nodes at Lagrange points, forming a hack-proof backbone for the solar system's future internet. Mars-to-Earth video calls could one day be encoded in particles that fundamentally cannot be tapped without leaving evidence. The implications go beyond security. Quantum networks could sync atomic clocks across worlds with unprecedented precision, enabling GPS-like navigation on other planets. Or imagine distributed quantum computing colonies pooling processing power via entangled particles to solve problems no single planet's computers could handle alone. China's follow-up to Misha's, the 2030 QKD constellation, aims to blanket Earth in quantum security. Its successor might extend that shield to astronauts planting flags on distant worlds. Yet the greatest breakthrough might be philosophical. Quantum communication forces us to confront the universe's strangeness, particles that mirror each other across light years, messages secured by the laws of physics itself. In an era where data is the new gold, these satellites aren't just tools, they're testaments to humanity's ingenuity in harnessing the cosmos' deepest mysteries. The interplanetary internet won't just connect machines. It'll bind worlds together with threads woven from the fabric of reality. From robotic bees buzzing through Martian skies to telescopes capturing alien oceans in another star system, these 30 missions represent more than just scientific milestones. They're stepping stones toward a future where humanity isn't confined to Earth. Each one cracks open a new frontier. Artemis paves the way for lunar cities, Dragonfly deciphers the chemical poetry of Titan's dunes, and Lisa listens for the universe's hidden symphonies in spacetime itself. Whether it's Da Vinci plunging into Venus's acid clouds or Starshot's light sails racing toward Alpha Centauri, these projects don't just push boundaries, they erase them, turning science fiction into blueprints for reality. The ripple effects could redefine our place in the cosmos. Finding microbial fossils in Jezero craters' rocks might prove we're not alone. A successful lunar elevator could slash the cost of off-world industry, making Mars a reachable backyard rather than a distant dream. And if quantum networks link planets with unhackable bonds, entire civilizations could rise across the solar system, connected by threads of entangled light. Even the failures will teach us. Every exploded prototype, every rover lost in dust storms, Every signal that fades into darkness is a lesson etched into the next attempt. This isn't just about rockets and robots, it's about rewriting what's possible. The James Webb Telescope already shows us newborn galaxies. Habitable Worlds Observatory might soon point to a planet where forests sway under alien suns. Psyche could reveal how Earth's core was forged, while space-based solar farms beam clean energy back home. And when astronauts finally sink boots into Martian mud, their footprints will trace a path blazed by 30 missions and countless generations of stubborn, starry-eyed dreamers. So now it's your turn. Which of these cosmic leaps ignites your imagination? Is it the subterranean oceans of Europa or the warp drive whispers of Breakthrough Starshot? Drop your pick in the comments, and if you're hungry for more deep dives into the final frontier, hit subscribe. The universe isn't done surprising us. And neither are we.